Now we would like to compute the derivative for the inverse hyperbolic secant. In the last video, we showed that the inverse hyperbolic secant of y is the natural log of the quantity 1 plus the square root of 1 minus y squared divided by y, where y lives between 0 and 1. So again, you can utilize the calculus of the natural log, or you can use the inverse function theorem. And since I've been using that with all of the calculations, I'll use it for this. And plus the practice that you get using the inverse function theorem is very good. So now, by the inverse function theorem, the derivative of the inverse hyperbolic secant evaluated at y is just 1 over the hyperbolic secant of x derivative. So it's easy to state, it's easy to remember. And we just computed this. This will be -1 over the hyperbolic secant times the hyperbolic tangent of x. We have our x in the red box up here. And so here are the formulas for the hyperbolic tangent and hyperbolic secant. So we have our negative, and of course this will have to be flipped. So now notice when we substitute x, the natural log and the natural exponential absorb, and we're just left with the argument. And we've seen this before in the previous calculation. So we have the argument here, 1 plus the square root of 1 minus y squared divided by y. And then the negative here will flip the argument, and we get y divided by 1 plus the square root of 1 minus y squared. And then, of course, the 2 is downstairs, and that's where I just put the negative for now. Now, with the hyperbolic tangent, this gets flipped. And so the numerators will be the same. It's e to the x plus e to the negative x. So again, we get 1 plus the square root of 1 minus y squared divided by y plus 1 divided by 1 plus the square root of 1 minus y squared. And then downstairs, the same terms, except now we have a negative sign. So we have 1 plus the square root of 1 minus y squared divided by y minus y divided by 1 plus the square root of 1 minus y squared. So it's like the same thing many, many times over. Now what we want to do is just get a common denominator, and of course it's y times the quantity 1 plus the square root of 1 minus y squared, which we have here. And so we'll have to multiply this by itself, and then to make this commensurate, multiply the y by itself. So we just get 1 plus the square root of 1 minus y squared quantity squared plus y squared divided by our common denominator. Now, the common denominator over here is the same, but once we get the common denominator upstairs and downstairs, it absorbs. And what are we left with? Well, the same type of computation. We'll have 2 copies of the 1 plus 1 minus y squared here, as we do over here, and of course 2 copies here, the y squared. And downstairs we'll have the same thing except for a minus sign. So notice here, the denominator survives, but here the denominator absorbs between the numerator and the denominator. So the algebra is fairly simple. You just have to look for the patterns and move it forward. Now, all we want to do, we've got our -1/2, and then hopefully a lot of this will absorb, so we're going to expand this binomial, expand all the binomials where it makes sense to do so. And let me just go ahead and put this in here. We've got the minus, and I left out my square. There we go. So here, when we expand this, we'll get 1 plus 2 times the radical 1 minus y squared plus 1 minus y squared when we square the radical plus the y squared that's already there. And then, of course, downstairs, we have the common denominator, y times 1 plus the square root of 1 minus y squared. And now, of course, over here, this is the duplicate of this. And so we get the same terms. 1 plus 2 times the square root of 1 minus y squared plus 1 minus y squared plus the y squared that's already there. And then, of course, downstairs, everything is the same except for the minus. Instead of plus y squared, we get the minus y squared. So very subtle differences. But now notice here, the y squares absorb, and we get 2 and 2. So we get 2 copies of 1 and 2 copies of the radical. So I just go ahead and factor the 2 and write 1 plus the square root of 1 minus y squared. Same thing for this side. We get the same thing, 2 times the quantity 1 plus the square root of 1 minus y squared. And now, of course, downstairs here, since the y squares don't absorb, we have two copies of everything, but now we have the additional minus y squared here. But upon factoring all these 2's, notice these 2's absorb and these 2's absorb. And notice these two factors here are absorb each other, and we're left with the negative divided by y right here. So that pretty much all goes away. And we've seen this calculation before. This will factor into the square root of 1 minus y squared times 1 plus the square root of 1 minus y squared. So again, we see that the same types of algebra and computations come again. That is, we see all of these similar calculations when we work with the hyperbolic functions, just like we do when we work with the standard trigonometric functions, and that's not surprising. And so now, of course, these two factors will absorb, and we're left with negative 1 divided by y times the square root of 1 minus y squared. And that, indeed, is the derivative of the inverse hyperbolic secant evaluated at y. Now what we want to do is extend to make it more user-friendly, so let u be a differentiable function of x. And of course now we don't want to divide by 0, so u would live between 0 and 1. Then by the chain rule extension, we would have the derivative of the inverse hyperbolic secant of u will be the negative of u prime, of course the chain rule extension, divided by u times the square root of u minus u squared. So now we have a derivative formula for the inverse hyperbolic secant, which will now provide us some very, very elegant integral theorems like we got with the inverse hyperbolic sine and inverse hyperbolic tangent. And we are done.